All right, we shall begin. Happy Monday. Happy day before Halloween. All right, we're gonna introduce Markov chains today, so that's exciting. All right, I wrote motivation. I don't know if this, I don't know if any of this is motivating, but let's see. Okay, so just kind of taking a big picture look. I think a lot of the reason why we even do Monte Carlo stuff in the beginning is because we want to be able to do Bayesian stats. And in Bayesian stats, we often want to find the expected value of a function or estimate some kind of integral. And, when you want to find the expected value of a function, you have some kind of random variable. And we said, it's too hard to solve this integral analytically. And so we can get a good estimate doing some kind of Monte Carlo method here. But, Monte Carlo, we have to be able to generate random values of that particular distribution. And we've covered a few kind of methods as far as generating random values. We had inverse CDF, we saw convolutions. I guess a thing that we could also throw in there was the transformation, the Box-Mueller transformation, and then as well as rejection sampling. So, inverse CDF is effective and efficient, but finding that CDF and inverting it can be a challenge. And then rejection sampling doesn't require finding the inverse CDF, but it can be inefficient, and I want to show you some examples where it would be inefficient. So let's say you wanted to generate values from the t-distribution, okay? And let's say we do the t-distribution with 3 degrees of freedom, and we're going to also fold it, all right? So we have the folded normal, but now we also have the folded t-distribution. And so the t-distribution, normal distribution, similar, but the t-distribution has heavier tails, right? And so if you look up what is the formula for the PDF of a t-distribution, it looks like this, okay? 6 root 3, I don't know where these numbers come from. 6 root 3 over pi, and apparently that is the constant needed to normalize the thing. And so, what worked for the folded normal was we said, hey, let's generate from the exponential distribution, and if we and that worked for the folded normal. And we'll say, okay, well, if we generate values from the exponential distribution, can we, do rejection sampling or something to get values from the t-distribution? Okay, they both have the same support. They're both generate values that are positive, okay? So our design should work in theory, but it doesn't because one thing that we need in order to do rejection sampling, we have to find an m so that g of x is greater than f of x for all x. And the way we find m is we find, okay, what is f of x, the desired target PDF, divided by g of x, our proposal PDF. And we want to find kind of the maximum value here. And when we do this, we run into a problem, okay? The tail of f of x decays on an order of x to the 4, right? So you look at whatever this thing is in the denominator. In the PDF, we're going to have x to the 4, while the tail of g of x decays at basically e to the negative x, right? So this is 1 over e to the x. So we have an x to the 4 versus e to the x in the denominator. And so our target PDF, the t-distribution, 3 degrees of freedom, is heavy-tailed. And so basically our max, this m, is going to be infinity. And no matter how big of an m you choose, as x gets bigger and bigger, m times g of x eventually will be less than f of x. And so we can't do rejection sampling, because the whole idea of rejection sampling is we're generating values from some kind of enveloping distribution, and the target distribution kind of fits neatly inside of it, right? So the idea was, if this is f of x, if f of x is in red and g of x is in orange, what we do is we take g of x, we multiplied it by some constant, and we wanted this red distribution to fit inside the proposal distribution. And this worked for the folded normal distribution, right? So here I said, let's multiply by 1.5. And if we do that, it looks like the red distribution fits inside the blue distribution, okay? And this looks like it's going to work. But then if we zoom in over here, we find that the blue crosses below the red distribution, and we are generating from the blue. So basically, once we go past, say, 5.5, we're never going to be generating enough values from g of x to kind of match up with the heavy-tailed nature of the t distribution. So that's with m equal to 1.5. So we could say, okay, well, what if we make m bigger, and we say m is 2, okay? And so now we can see, the blue distribution is even taller, the red distribution is even shorter. So this was at 1.5, and you'll see that, the red distribution shrinks comparatively. And again, this fits over here, it fits very comfortably inside the blue. But then again, if we zoom in this area, again, it crosses, right? So now values above, say, 6.4 will not be generated frequently enough. So we could try, all right, what if I keep doing a bigger value of m, right? M equals 6, okay? And so this works, but eventually until we get to, say, like 8.5, and then we're not generating enough. And, just for fun, I said, hey, let's do m equal to 60, okay? And so, comparatively, the distribution that we're generating from in blue looks like this. And we're only going to accept values that fall under the red line, okay? So we're only going to accept a very small proportion, okay? And these lines don't cross until you go beyond 12. But if you do zoom in beyond 12, they do cross, okay? They do cross. And so, we still won't be generating enough values. But you might be like, okay, well, 12, come on. Even for a t distribution with a heavy tail, we're not going to be generating values above 12. So it doesn't really matter, okay? And that's probably true, right? The probability of generating something above 12 in a t distribution with 3 degrees of freedom is, probably on the order of like less than 1 in a billion or something. And so you could say, well, okay, that'll be accurate up until x is 12. Which is fine, but I wrote accurate for approximately 0.995 values. Okay, so I guess okay, not in 1 in a billion, but the problem here is, again, we're only accepting those that fall under the red line, okay, which is going to be a very small proportion. We're only going to accept around 1 in 60 values, because the amount that you accept is around 1 over m. So, and just to kind of illustrate, indeed, that is the case, okay? So I just run some code to do rejection sampling, and I have m equal to 60, all right? So here, f of x is the t distribution, PDF of the t distribution times 2, because we folded it in half. The proposal distribution is the exponential distribution, and we're going to propose 100,000 values, 10 to the 5. I'm going to generate 100,000 uniform values. We're going to calculate this ratio. We're going to accept from wherever u is less than r. And then we say, okay, how many values did I accept? And out of 100,000 values proposed, we accepted 1,600, okay, 1,609. So we rejected like 98% of these things, okay? Which not great, okay? But, you know, we look at the 1600 values that we did accept, and yeah, it looks like the kind of the t-distribution. And if we wanted to generate like from the full t-distribution, so remember we've created the folded t-distribution, and then to kind of go from a folded t-distribution back to like a regular t-distribution, we could just flip a coin and say half of these values are going to be negative and half of these values are going to be positive. And so here I can just say sample 1 or -1. And then when we do that, this looks like the t-distribution. And we can do a KS test to see if it does follow the t-distribution. And I say, you know, take our random, the values that we generated, random values, compare it to the CDF of the t-distribution with 3 degrees of freedom, and we get a p-value of 0.68, so that we say right now with 1600 values generated, we have no evidence, or we don't have evidence to reject the null hypothesis. So I don't have any reason right now to believe that our data is coming from something other than the t-distribution with 3 degrees of freedom. So our method, rejection sampling, does work, but again, we had to generate 100,000 of these values just to accept around 1,600 of them, right? And so, so I wrote a pro. It seems like our method is working, but it is very inefficient, and it won't produce correct values if x is greater than, say, 12.275. Okay, there is a transform kind of based on the Box-Mueller that does work for generating values from the t-distribution, and you can read academic articles about that. So, you know, as far as the t-distribution goes, you know, we do have a method. You could also do the convolution, where you basically have a normal distribution and you also get a chi-square distribution, and then you kind of combine those things and divide them out to get a thing. But we're going to say this is a opportunity or whatever. One of the things we can do to kind of solve this problem is Markov chain Monte Carlo, right? So I wrote, the modification of the Box-Mueller transform is an elegant solution for generating values from the t-distribution. There are many other scenarios where rejection sampling is inefficient and such a transform solution doesn't exist. And then when you go to higher dimensions, rejection sampling can also become very, very, very inefficient. So, you know, so far all of our methods have been pretty much univariate. We had like one lecture doing like bivariate stuff. But yeah, in higher dimensions, which is a thing, right? Sometimes we have distributions that exist in like, I don't know, 20 dimensions or something like that. And rejection sampling in those cases can become really, really, really inefficient. So we're going to introduce Markov chain Monte Carlo. And Markov chain Monte Carlo is going to be a tool that we can use to produce random samples from the desired target distribution. Markov chain Monte Carlo, the samples it produces are going to be correlated, and so we can kind of like throw out half the values, or only keep 1/3 of the values or something like that to kind of decorrelate. There's this concept of like auto lag and things like that. But anyway, we'll get into it. All right. So before we can even get into the Markov chain Monte Carlo, we have to just talk about Markov chains to begin with. Do you guys take a class on Markov chains in like math or something? No? Okay, sort of. Okay. All right. So there are different kinds of Markov chains. We're going to start off with kind of a basic kind, and this will be a discrete time Markov chain. So we're going to have time at time at 1, time at 2, time at 3. So these are kind of like discrete time intervals. There's continuous Markov chains where like the time intervals aren't evenly spaced out or anything like that. But here we're just going to have the discrete time, and we say this is a stochastic process. Stochastic process is just a way to say it generates a sequence of random variables that satisfy what's known as the Markov property, okay, which is to say that at time n plus 1, okay, the random variable x at time n plus 1, given everything that came before it, okay, can be simplified to just the random variable at, so given everything before it, so starting from, I guess, the beginning of time at time 0 up to xn, okay, can be simplified to basically the random variable at time n plus 1 given the state at time n, okay? So our lives as people are not a Markov chain, right? Like who we are today kind of depended on like what happened yesterday and what happened the day before, and like you had events in your childhood that kind of shaped who you are and things like that. So like, what happened back here on these days, like they have an effect on like today, okay? But there are other things where what happens today only depends on what happened yesterday, okay? And everything that happened prior to yesterday doesn't matter. Okay, that's basically what the Markov chain says, is that we can erase basically all of the history from x0 to x before xn, and we only look at basically at time at xn to figure out the probability at time n plus 1. So, what happens at time n plus 1 only depends on the value at xn, okay? That's the Markov property. Is that, the probability at state n plus 1, or time n plus 1, only depends on the time n. Okay, let me give you your first view quiz answer. The letter D. D as in dog. D as in dog is their first view quiz answer. We have also the state space of the Markov chain, and that is all of the possible values that our random variables can take on, right? So if you have like a coin, your state space is heads or tails, okay? If you have a dice, your state space is like the numbers 1 through 6. And if you have something else, your state space might have like a whole bunch of different things, okay? So we'll start off with kind of discrete time, and then we'll start off with a simple discrete state space as well. But we can have continuous state spaces or things like that. Okay, so yes, the Markov property means that the probability that the chain moves to state, say, j on the next state only depends on the current state I, not on where the chain has been previously. And we will only consider Markov chains with countable or finite state spaces. So we're going to start off with the discrete state. So basically, we can list off all of the possible values that the Markov chain can take on, and at discrete times, right? And again, there's more kinds of Markov chains where you can replace discrete with continuous and things like that. So because it's a discrete state, we can write out the state space, and if it's countable but goes on forever, it will be 0, 1, 2 going on forever. Or we'll start off with the finite case where there's an end to how many of these things that we can be. Markov chains are kind of defined by our transition probabilities, which are these conditional probabilities that are defined as basically what's the probability that at time n plus 1 we're going to be at state j, given that at time n we are at state I, okay? And so we're going to figure this out for all states I and j. So Markov chains, I guess, if you just have a sequence of independent variables, there's no need to use a Markov chain, right? We're basically saying where you are now has an influence on where you're going next, okay? So we'll often organize all of these transition probabilities into a transition matrix. And we'll call this transition matrix P. And so everything's a probability, okay? All of the entries in this transition matrix are non-negative. They can be 0, okay? But they are non-negative. And the sum of each row in the transition matrix has to add up to 1, okay? So the way we read this is, this top left, P00, is the probability of of basically moving to state 0 if you are currently in state 0, okay? So your current state is I, so these are probabilities ij. So your current state is 0, and we're asking what is the probability you move to j? So if we are currently at 0, what's the probability that at the next state, at the next time, we remain at state 0? P01 is the probability, if we are currently at 0, what is the probability that we will move to state 1? This one is if we are currently at state 0, what is the probability we move to state 2, and so on and so forth. And so therefore the entire row covers basically all of the outcomes that could happen if we are currently at state 0. If we're currently at state 0, we have to go somewhere, even if it's remaining where we are, we have to end up somewhere. So the entire row has to add up to 1. Okay, all of the probabilities in a row have to add up to 1. Okay, this next row, P10, is if I'm currently at state 1, what's the probability I go to state 0? P11 is if I'm currently at 1, what is the probability I go to or remain at state 1, and so on and so forth. And again, wherever we are, Pij, if we're currently at I, okay, if our value at time n is equal to I, what's the probability at time n plus 1, we go to j. That is how we read this transition matrix. So we will start off with kind of the simplest possible case for a, I guess, discrete time, discrete state Markov chain, which is that we will have 2 states, okay? So that's about as simple as we can get. And so we have 2 states, state A, state B, and there are 4 arrows indicating basically our transition probabilities. So we can start off at state A, and we can go return to state A, or if we can start at state A and we can transition to state B. Or we can start at B and we can return to state B, or we can start off at B and go to state A. So these are the 2 states, and there's basically 4 values that we have to figure out. And so just to kind of keep it very simple, we're going to say state A is sunny weather. So I guess this could be like California, all right? Sunny weather will be state A, and if it's anything other than sunny, so whether it's cloudy, rainy, or overcast, I don't know, something that's not sunny, we'll call that state B. And we can kind of treat this kind of like a Markov chain, right? And we can say, if today is sunny, then the probability that it will be sunny tomorrow will be 70%. And if today is sunny, the probability that it's not sunny tomorrow will be 30%. Okay, so our row adds up to 1. Okay, on the other hand, if today is not sunny, if it's cloudy or whatever, the probability that it's not cloudy tomorrow will be 60%. And if it is not what did I say? This probability, if it's not cloudy, if we're in state B, the probability that we're in B tomorrow is going to be 0.6, and the probability that it becomes sunny tomorrow will be 0.4. Right. So this is about as simple of a Markov chain that we can produce, and we have 2 states And our transition probability matrix is this 2 by 2 matrix, indicating our transition probability of starting here and going, to the next. And again, each row, the probabilities add up to 1. All right, so this defines a Markov chain just by kind of creating this transition matrix. And if you have a transition matrix, basically you've defined a Markov chain. All right, here's another example. This is known as the Ehrenfest-Ern model. And so we'll kind of develop the transition matrix to create our Markov chain here. So the Ehrenfest-Ern model is kind of this model that can be used to model, I guess, diffusion of molecules through a membrane. I don't know, all right? But you imagine like, what is it? Like in biology, you have a cell, right? And then like nutrients and molecules pass in and out of the cell membrane, right? Animal cells have membranes and plant cells have walls, I think. I don't remember. Something like that, right? Okay, but anyway, we're going to just say we have 2 urns. We have urn A and urn B, and we're going to say within this system, there's a total of n balls, and these balls represent molecules. Okay, and at each step, we are going to randomly choose one of these molecules or one of these balls and move it from move it to the other urn. Okay, so this is just to say at any given time, a molecule can pass through the membrane, either from the outside coming in or from the inside going out. Okay, and so we're going to say our random variable x at time n denotes kind of the number of molecules or balls that are in urn A, all right, which means we have capital N minus xn in the other urn. And the possible values for x sub n is going to be basically 0, 1, 2, 3, all the way up to capital N. And we're going to try to figure out what is our what's basically the transition probabilities for the sequence of how many molecules or how many balls are in the urn, okay? And within our kind of, the sequence for our Markov chain with this particular state space. So let's say we have I balls in urn A at step n. And so if we know x of n equals I, then at the next step, the only possible values that we can take is either we have like one molecule came in and we now have I plus 1, okay, at the next step, or a molecule from A leaves and we're at I minus 1. Okay, so those are the only two things, right? Because we're just looking at one thing entering or one thing leaving. So we're not going to jump from I to I plus 2, and we're not going to remain at I. So either one comes in or one leaves. So at the next step, we're either at I minus 1 or I plus 1. Okay, and if the ball that's chosen or if the molecule leaves A, then at the next step, we're at I minus 1. If it comes in, we're going to be at I plus 1. And the ball that is just randomly chosen among all of the n molecules or n balls that exist in this entire system, and we're going to say every single one has the same probability. So the probability that a ball is chosen from a particular urn is proportional to the total number of balls in that urn. So here is kind of a diagram illustrating, let's say we had a total of 4 molecules, just to kind of keep it simple. So we have 4 possible things that could happen. So we're going to start off and say we have 2 molecules in A and 2 molecules in B, okay? Or 2 balls in A and 2 balls in B. And so if I choose this one from A, okay, at the next step I will be down to 1 in A and we'll have 3 in B, okay? And then if I choose this one from A, at the next stage, we'll be down to 1 in A, and then we'll have 3 in B. If we choose this one, we'll go from 2 up to 3. And if we choose this one over here, our random variable representing how many balls we have in A will go up to 3 as well. So counting how many so we have 4 possible transitions, and of these, 2 of them result with 1 left in A, and 2 of them result with 3 in A. And so the probability of ending up at 1, so the probability that at time n plus 1, we have 1 value or 1 ball in A, given that we started off with 2, is going to be 0.5. And the probability that at time n plus 1, we have 3 balls in A, given that we started with 2 balls, is going to be 0.5. So our transition probabilities are going to be probability going from 2 to 1, so P21 is 0.5, and the probability of going from 2 to 3, or P23, is going to be 0.5. So that's pretty simple. Okay, what if we started off with 3 balls in A? Okay, if we have 3 balls in A, then we can go from 3 to 2. We can pick this one and we go from 3 to 2. If we pick this one, we go from 3 in A down to 2 in A. And if we pick this one, we start off at 3 in A and we go down to 2 in A. Okay, and then, but there's a probability that we pick this ball, because we're picking one of the 4 balls at random, and we would go from 3 in A up to 4 in A. So the probability that we end up with 2 balls in A, if we started off with 3, is going to be 3 out of 4. So probability P32 is 0.75. And the probability that we end up with 4 balls in A, if we started off with 3 balls, is going to be probability 3/4, which is 1/4, 0.25. Okay? So does that kind of make sense as far as these transition probabilities go for this EARN model? So we have 3 ways to go from 3 down to 2, and we have 1 way to go from 3 up to 4. Okay, and so you can kind of take this and figure out the transition probabilities for all of the other states. So we illustrated basically P21 is 1/2 and P23 is 1/2. The other ones are going to be 0. P32 is 3/4 and P34 is 1/4, and the other probabilities in that row is going to be 0. And then again, you can figure it out for the other ones. If you started off with 4 balls in EARN A, then you have no choice. Like if you pick one random ball, it's going to come from EARN A, and you're going to end up with 3 at the next step. So probability P43 is going to be 1, and then we have 0s everywhere else, and similar logic applied to the other ones. So this is going to be our transition matrix if we have a total of 4 balls or 4 molecules in our entire system here. So that's what the transition matrix to define our Markov chain will look like for the Ehrenfest EARN model. Oh, okay, and then I guess I drew a diagram and I don't know what happened. It got all stretched out. But here we say, okay, if we started off with 2 balls in the system, we have a probability of 1/2 going up to state 3, and we have a probability of 1/2 going down to state 1. Okay. If we start off with 3, we have a probability of 1/4 going up to 4, and a probability of 3/4 going down to 2. And so this is just kind of a diagram representing our whatever this transition probability matrix. If we start off at 4 with probability 1, we go down to 3, and so on and so forth. So this is kind of this is what this Ehrenfest EARN model looks like. As this kind of state diagram with arrows. We can go from 0 to 1 basically, or 1 to 2, or 1 to 0. Other models might have more arrows, where you can, if we allowed for 2 molecules to pass in at the same time, we could jump from 0 to 2, or jump from 1 to 3, or 1, we would have arrows that connect all of these different states. But here we're going to just say, we can only basically go to only the adjacent states or something like that. Okay. So this is what the transition probability diagram might look like. Okay, if we wanted to generalize this to just kind of for any number of balls n, then the transition probabilities that we move down to, if we currently have I balls in urn A, the probability that we move down to I minus 1 is basically the probability that we select a ball from urn A, which will be I divided by n. If there's a total of n balls in the system and I of them are in A, the probability that we select a ball from A is going to be I over n. And if we select a ball from A, we're going to end up at I minus 1. And then the probability that we go to I plus 1 means we selected a ball that wasn't in urn A. And so that's going to be the complement 1 minus I over n. And then moving to anything else is going to have probability 0. And so all of the values in the transition matrix can be defined with this kind of rule. It's going to be I over n, or 1 minus I over n, and 0 otherwise. Okay, I over n if we're talking about the next state being I minus 1, and then it's 1 minus I over n if we're looking at the transition probability of going to I plus 1 at the next state, or the next interval. Okay, so that's another transition matrix Markov chain, and then we'll do one more Markov chain here. We'll have a random walk. Okay, and so this random walk can be used to kind of model the path that an object or a particle takes as it moves through space. And so we can say, particle, so Brownian motion. If it's continuous time, we have Brownian motion, which is kind of like, how does a particle like move inside like a liquid or a gas or something like that, right? You have a path that an insect can take as it searches for food. A gambler's winnings or losses can go up or down. Stock prices can also be regarded as random walks or things like that. And we're going to just look at a very simple one-dimensional random walk, okay? So basically, we're looking at something like stock prices or winnings or losses, where basically you have a number and it's either going to go up or down or something like that, okay? And so we're going to have this process, stochastic process, sequence of random variables, x0, x1, x2, so on and so forth. And we'll keep it simple, and we'll say these values come from, we'll just look at integer numbers, and we're going to start off at 0, and at each step, either we move one value up or one value down, okay? At each step, the random walk moves to the right 1 unit with probability p, moves to the left 1 unit with probability 1 minus p, okay? So, 1 step to the right, 1 step to the left, something like that. All right, and so if we start off at 0, then at the next time, x at time 1, we're either going to end up at 1 or negative 1. Probability we end up at 1 is p. Probability we end up at minus 1 is going to be 1 minus p, or q. All right, and then, if we're at some random time in the future, okay, we could be at some value, let's say, 100 or whatever. And if we're currently at 100, then we can end up at 101, or we can end up at 99, right? And so we end up at I plus 1 with probability p, or I minus 1 with probability q. And so to just kind of more generalize this to just any values I and j, we're going to say if we're currently at I, at time n, we're currently at I, the probability that at time n plus 1 we end up at j is going to be p for j equals I plus 1 is q, or 1 minus p for j equals I minus 1, and it's 0 everywhere else, okay? So in this kind of random walk thing, we're not going to be able to create the transition probability matrix because it's infinite, right? As everything is our integers, but we have basically a rule for the transition probabilities, and that's good enough to kind of define the Markov chain. This random walk can also be expressed as a sum of independent random variables, right? And so we can just say, hey, we have a sequence of independent random variables, that are, sequence y, y1, y2 of independent random variables. And basically, we're just doing a whole bunch of Bernoulli draws. My batteries just died. So we could, say we have basically these Bernoulli draws of, but it's going to be 1 and -1, getting basically 1 with probability P and -1 with probability Q. Okay, and then and we're going to say we can have the Markov chain. We're going to start off at x0, and then xn is going to be equal to the previous state, x at time n minus 1, plus whatever y sub n is equal to, either a 1 or a -1. Okay, so let's just kind of illustrate what this could look like if we were to run some code. So here I'm going to just generate 1,000 steps. Our probability P is 0.5 and Q is 1 minus P, or also 0.5. And we're going to just sample random values, either 1 or -1, okay, with these probabilities with replacement. We're going to ask for 1,000 of them, and then we'll just kind of take the cumulative sum of all of these things. And so for set seed 1, this is what my random walk looks like, okay? And so, when you kind of flip a coin, you feel like, oh, we should get half heads and half tails and things like that. And overall, if you kept track of your sequence, we should be at around 0. But we deviate, right? So sometimes we get a bunch of tails in a row, and so we had a kind of a stretch where we had a whole bunch of tails, and it just kept going down and down, 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 and then we go up, down, up, down, up, down, whatever. Okay. And so after around 500 and after around 1,000, after around 500, we're at x equal to -40. And then you do another 500 and we're still at x equal to -40. But, this is a random walk going either left or right, something like that. Okay. If I just pick a different random seed, here I end up at, x equal to 50. Okay. Going up and down. And so this is just a random walk, Markov chain. Basically, what's the probability I end up at 50, okay, at some particular moment in time, basically only matters on the previous state, all right? So, if I was previously at 49, I have a 50% chance of going up to 50, and I have a 50% chance of going down to 48, okay? Obviously, if I start off at say 0 or start off somewhere else, the probability that I end up at 50 at some particular time is much more difficult to calculate. But as far as the Markov chain goes, we're just really only concerned with what happened in the previous state. Okay, the probability of the next time, because we can Markov chain, we really can only look ahead 1. Okay, everything else, it kind of depends on everything that happened before it as far as ending up where you have, but given the current location, we can figure out the probability of kind of our next thing. Okay, so that's kind of an introduction to Markov chains. And how does this relate? Remember, our big picture goal is we want a Monte Carlo method out of this whole thing, where we can kind of generate values from a desired distribution. So far, we've just been talking about Markov chains, which is just like, okay, a sequence of random variables where the next value depends on their current state. Okay, so the key idea here is that Markov chains, well, some of them have what's known as a limiting distribution, All right, let me give you your next view quiz answer. The next view quiz answer is the letter C. C as in cat. C as in cat. So to kind of bring about this idea of a limiting distribution, let's revisit the two-state Markov chain. So this time I've got slightly different probabilities, okay? But I've got state 0 and state 1, and these will be our transition probabilities. If we're currently at state 0, we'll return to state 0 with probability of 0.8. If we're currently at state 0, we'll transition to state 1 with probability 1. Okay? And if we're currently at state 1, we will return to state 1 with probability 0.4. And if we're currently at state 1, we will transition to state 0 with probability 0.6. Okay, so looking at this, if we were to just allow this Markov chain to run for a long time, are we going to end up in state 0 or state 1 more often? We're going to end up in state 0, right? Because when we're in state 0, we remain in state 0 80% of the time, right? So more than half the time if we start off at state 0, more than half the time we end up staying in state 0. And then if we're currently in state 1, we end up transitioning back to state 0 more than half the time as well, right? So the only way we end up at state 1 is if we transition from state 0 to state 1, which only happens with probability 0.2, or we remain at state 1. We're currently at state 1 and we remain at state 1, which happens with probability 0.4. So just kind of looking at this transition probability matrix, we can see, oh yeah, if we let this kind of Markov chain run, you're currently at state 0, where you end up next, and we just kind of let it run for a long time, we can see most of the time we're going to end up in state 0. But what we'll do is we'll actually run the Markov chain and just kind of see what happens. So we're going to just let it run for a long time. This is not really a long time. This is just 1,000 draws from the Markov chain. But let's just kind of see what happens, okay? Here's a little picture of this thing. Okay, so here's my transition matrix. 0.8, 0.2, and 0.6 and 0.4. And so, can I make this bigger? Okay. So here we've got state A and state B, or state 0 and state 1. And we can see a lot of times we end up in state A and it just kind of goes to state A. And you can see sometimes it goes to B. And then if it goes to B, it often goes right back to A. Sometimes we're at B, we'll stay at B. Let's see. I'm just waiting for, so if we record, what happens, we're going to see, okay, we end up going to state A a lot, right? Sometimes we generate from B. Okay, but anyway, this is basically what a Markov chain kind of looks like when it's, I guess, an illustrative thing. Here's the code, all right? So here I have this matrix. First row is 0.8, 0.2. Second row is 0.6, 0.4. And if you, R's default is to kind of fill in the matrix column-wise, which can be annoying when you're trying to do something. So the trick is to use rbind, which will bind rows, and you can just write out your the vectors of what each row is. Okay. I guess here I said I want 100,000 of these things. And we're going to start off at 0, and then I have 99,999 missing values, NAs, and we're going to kind of fill these in. So we're going to say for I at time 2, because we already have a value at time 1, which is 0, what are we going to do? Okay, I'm going to take our current value, okay? Our current value is going to be x at time I minus 1, okay? Or I guess our previous value, I should say. So if we want to figure out what we're going to be at time 2, we take the value at time 1. So we take the value at I minus 1. And then, so remember the values at time I minus 1 are either a 0 or a 1. And so if we're at 0, we want to pick the first row. And if we have a value 1, we want to pick the second row. Okay, so I say the row that we're going to select is going to be whether a 0 or 1, and we're just going to add 1 to it. Okay, so that's what this line represents. And then I subset to that particular row, and I use that to generate a 0 or 1 using ours, what just happened here? Okay, using R's sample function, right? With the sample function, you can specify the probability corresponding to these values. So we're going to say sample is 0 or 1 using the probabilities from the selected row. So either use a 0.8, 0.2 to generate a 0, 1, or if we're in the second row, if our previous state was a 1, use a 0.6 or 0.4 to generate a 0 or 1. Okay? And so I let the Markov chain, so this is it, okay? This is the code for generating producing a Markov chain. Very simple, right? It's just kind of like, what's your current value? Okay, or I guess, what was the value at time I minus 1? And use that to generate the value at time I. And so we do this, and then I say, okay, well, how frequently did we end up at state 0? And so out of the 100,000 values, 10 to the 5, I ended up at state 0.7497, so 74,970 times out of 100,000. And then I ended up at state 1, 25,030 times, or with a probability of around 0.25, okay? So that's if I started off at state 0, and I use set seed 1. Okay, here I'm going to start off at state 1. Does this make a difference? If I start off at state 1, I'm going to use a different random seed. So I'm running the same code using basically what was our state at time I minus 1. I add 1 to that to figure out which row I'm going to use for my probabilities. And then so for the probabilities, I use the probabilities from that row in the P matrix to generate either a 0 or 1. And I do this, and after 100,000 runs, I get a probability of 0.74685, so just under 75,000, 74,685 times we ended up at 0, 25,315 times I ended up at state 1. So just kind of looking at this, so starting off at state 0, these were my probabilities, and starting off at state 0, or state 1, these were my probabilities. And so just kind of guessing a little bit, one chain started at 0, the other chain started at 1. Both Markov chains ended up with approximately 75% of the time we end up in state 0, 25% of the time we end up in state 1, okay? And we can say, is there a probability? We're going to call this pi 0, which is the long run relative frequency that the chain visits state 0. And then we have pi 1, which will be the long run relative frequency that the state ends up, that the chain is in state 1. We could have this, we can say, what is our stationary or limiting distribution, right? Which will be kind of this vector pi. Basically, what is the probability we end up at state 0 or 1? And just kind of from looking at our simulation, we might guess that the limiting distribution is 0.75 at 0 and 0.25 at state 1. Okay, so this is just kind of, I ran it twice and we said, hey, it looks like we end up at state 0 75% of the time, and it looks like we end up at state 1 25% of the time. And I don't know, we can kind of, I guess we can watch the animation or whatever and just kind of keep track in our head how often we end up at one of these states versus the other. Okay, I don't, state A versus state B, and we can let it run. It's going too fast to count, but 0.8, 0.2, 0.6, 0.4. Okay, it looks like we're at A way more often, but I guess this is around 3/4 of the time, and this is around 1/4 of the time. So this is so we want to kind of have this thing known as the limiting distribution, and that's going to be the fraction of the time that state j, okay, is either pi j, right? If pi 0 is 0.75, then the Markov chain is in state 0 around 75% of the time. And so the probability that x at time n is in state j is going to be pi j, and we're going to say as n goes to infinity, the probability, what we want is to say that the probability that we end up at state 0 is going to be 0.75 regardless of what our initial state at time 0 was. Okay, so whether I start off at state 0 or state 1, we want to talk about what's the probability that I end up at state 0 at some arbitrary point in the future, state n. Okay, and so it's important that the distribution is independent of the initial state, because we want to say it doesn't matter where I start. Eventually, I'm going to end up towards this limiting distribution. So we're going to say this is going to be our definition of the limiting distribution. So we have this kind of probability distribution of all of the different possible, basically a vector of probabilities over the entire state space, okay? And we're going to say pi is the limiting distribution if as n approaches infinity, so as we go arbitrarily into the distant future, we're talking about the probability that we end up at state j, okay? Regardless of where we were in the beginning of time, okay? So regardless of what x at time 0 was, the probability that we end up at j at some point in the future is going to just be this value pi j. And so if this limiting distribution does exist, and it doesn't always exist, but if it does exist, then pi j represents the probability that at some time n, we're in state j, independent of the initial state, and it would be kind of the long run expected fraction of time that the Markov chain spends in state j, the long run thing, okay? And this stationary distribution, is basically our distribution over states, so that the expected distribution of the Markov chain at the next time remains the same, okay? Basically, it's if the Markov chain reaches this kind of this state of equilibrium, all right? And if there is a limiting distribution, that limiting distribution will be the stationary distribution, all right? And then there's something that, this property that we say if a Markov chain is ergodic, okay, then the Markov chain will eventually converge to a stationary distribution. So this is like just a whole bunch of new terms and stuff. But the idea is we're looking for Markov chains with this property, that I guess we can call it ergodic, where this Markov chain will eventually converge to a stationary distribution. Basically, that it has a limiting distribution, and that if you let the Markov chain run long enough, it's going to kind of converge over some kind of thing, all right? So, the random walk doesn't really have a stationary distribution because you can end up at technically plus infinity or minus infinity. And there's not like we can say, okay, after letting it run for a really long time, we can say we're going to end up with this distribution over like the integer numbers. All right. I'm going to just kind of give some informal definitions of Markov chains. Informal definitions, I guess, that apply to Markov chains, just because you could take like a formal class on stochastic processes and things like that, where you'll have like better definitions that are a little bit like more like proof-based and stuff. But here we're just going to kind of go for like higher level conceptual ideas here, okay? Without going through the too much mathy proof stuff, okay? We're going to just say a Markov chain is ergodic, has this thing if we can start the chain at any of our kind of starting locations, I, and that at some arbitrary point in the future, okay, not infinitely into the future, but just some arbitrarily finite value, and it might be like n equal, at time 1 billion, okay, but not infinity, okay, right? So it could be like the distant future, but not infinity. We're going to just say at some point in the future t that the probability in any of the other states are all strictly greater than 0, okay? So if it suddenly becomes like impossible to end up in a particular state, then that breaks this kind of thing, okay? So this must be true for all t greater than some finite integer t0. Okay, and so we're going to say the Markov chain, to be ergodic, it has to be irreducible and aperiodic. So a Markov chain is irreducible if all states communicate with each other, all right? And if a Markov chain is reducible, if it's not irreducible, which is kind of a silly thing to throw in there. But basically, that's what we're going to say, right? And we're going to say two states, I and j, communicate with each other if there is a path, even if it has to travel through a whole bunch of other states, if you can get to state j from state I, okay? So any two, if we can go from state I to state j, so if I start off at 0, can I end up at 3? And the answer is yes. I have to go through, in this thing, I have to go through 1, then 2, but I can end up at 3, right? If I start off at 3, can I end up at 1? Yes, if I go through 2, and so on and so forth. Okay, so this one is irreducible. All the states do communicate to each other. There is a path to go from any one state to any of the other states. This one is not irreducible. This would be reducible, okay? The states do not communicate with each other. If you start off at 0 or 1 or 2, there's no way for us to get to 3 or 4. Okay, there's no way to get for us to 3 or 4. And so, from 3 or 4, we can get down to 0, 1, or 2. But if we start off at 0, 1, or 2, there's no way to get to 3 or 4. And so we say this is reducible because if I start off at 0, 1, or 2, I might as well just throw away the rest of the chain, or the rest of our diagram. I can reduce our diagram just to 0, 1, and 2, and nothing would change, right? I wouldn't be losing any information about where our Markov chain would be going into the future if I start off at 0, 1, or 2. So we don't want that, okay? We don't want a reducible chain. We want something irreducible, all right? So that's one of the kind of conditions for our Markov chain to be ergodic. We need to be able to get to basically every other location in the state space. And then our Markov chain has to be aperiodic, okay? So what does it mean to be aperiodic? Well, we have to talk about what it means to be periodic in the periodic, which is kind of the greatest common divisor of the number of steps you can take and end up back at the state where you started. Okay, so this is a little bit weird. Okay, but let's say we start at state 3. If you have an irreducible chain, that means you can end up back at itself, right? So if you start off at state 3 and it's irreducible, you can go to state, say, 2 or 1 or some other location, and then all the states communicate with each other. So if you go to state 0, you can end up back at state 3. Okay, so how many steps does it take to end up back at state 3? Well, you can say, well, I can go from 3 to 2 and from 2 to 3. So it took me 2 steps, okay? Or you can go from 3 to 4, back to 3, back to 2, back to 3. And you can say it took me 4 steps to get back to 3, okay? Or you can go to 3, 2, 1, 2, 3, all right? And that also took you 4 steps. And you can kind of trace out any of these other paths, and it would take you an even number of steps, right? Can you get back to 3 in an odd number of steps? Okay, in this diagram, it is not possible to get back to 3 in an odd number of steps. It's going to be some even number of steps. And so we would say this chain has a period of 2. Okay, so the greatest common divisor for all of these things is 2. So, and that's going to be the case for basically all of these steps. And so, so this chain has a period of 2. If I add this one path where I go from 4 back to 4, well, with this, now I can start at state 3 and I can end up back at state 3 in basically any number of steps greater than 2, all right? So I can go from 3 to 4 to back to 3, 2 steps. I can go from 3 to 4, and then I can go from 4 to 4, and then back to 3, and that would take me 3 steps to get back to 3, okay? And I can go 3, 2, 1. I can take 4 steps to get back to 3. I could take 5 steps to get back to 3, right? Because I could just keep visiting 4 a whole bunch of times. And so in this case, the kind of greatest common divisor for all of these steps is 1, and we would say we have a period of 1 in that. So if we look at this chain, and if I tell you we started off at state 3, okay, at time 0 we started off at state 3, and I say, hey, we are at time 5, okay? At time 5, we know we can't be at state 3, okay, because it's odd, okay? Whereas over here, if I start off at state 3 and I say we're at time 5, well, you could be at 3, you could be somewhere else, right? You could be anywhere in the chain, right? So, so we want something that's aperiodic, where we can say, you know, at some time, arbitrary time, it's possible to be at any of the states, okay? Versus back here, if I give you, say, at time 5, you know it's only possible to be at some of the states and not other states, because you have this period of 2 where, you know, either we're going to either be at the even states or the odd states, right? And so, you know, because we can kind of quote abuse visiting state 4 as many times as we want, okay, even or odd number of times, we can see all of these states will have a period of 1. And so, you know, given wherever I start, if I just pick some arbitrary time in the future, we can end up at any of the other states, okay? So a Markov chain is aperiodic if all the states have a period of 1. And we're going to say a Markov chain is irreducible. If a Markov chain is irreducible and at least one of the states can kind of go back on itself, then the chain will be aperiodic. All right, so revisiting this kind of 2-state Markov chain, we can say we can achieve kind of like an equilibrium. This chain is irreducible. I can't reduce it to be anything smaller. And it's also aperiodic, because we can see, yeah, you know what? If I start off at time 0, I could be at state 1 or 0, you know, at any point in the future. All right, and we want to kind of find, you know, what is the stationary distribution when there's kind of this equilibrium between states. That is, the probability of transitioning from state 0 to state 1 is equal to the probability of kind of going from state 1 to state 0. Okay, we're not just talking about the transition probability matrix. Okay, going from 0 to 1 is 0.2, and going from 1 to 0 is 0.6. We're not just talking about this transition matrix, but kind of like given kind of the distribution over 0 and 1, what is our probabilities that we're gonna end up running out of time here. So let me just show you an illustration, and then I think we'll have to spend a little bit more time going over each of these things on Wednesday. But let me give you your last view quiz answer, which is going to be the letter A. A as an apple. A as an apple is your third view quiz answer. All right, so we'll go over this in a little bit more detail on Wednesday, but I want to. 0.8. Okay, so here is, if I start off at 0, I end up going back to 0 with probability 0.8, and I go to state 1. So this is California and New York. And I go to the other state with probability 0.2, and if I start off over here, I go with probability 0.6 over here and probability 0.4 over here. And so this will kind of, I can hover over this, and so 20% at any time, 20% of this thing is going to go over here, and over here 60% of the yellow will come over to the blue, okay? And so we achieve kind of this equilibrium when the amount going from the blue to the yellow is equal to the amount coming from the yellow to the blue, okay? I can start off with different starting populations. So I could start off with very few in blue and a ton of yellow, okay? And again, what we're gonna see is 20% of blue goes to yellow and 60% of yellow goes to blue. Okay, so I'm going to start here. 60% of yellow goes to blue, but then 20% of blue goes to yellow. And despite starting off with different quantities in the beginning, okay, what we find is that eventually we kind of reach a state of equilibrium where the amount going from blue to yellow is equal to the amount going from yellow to blue. All right, okay, all right, I'm out of time. I'll show you this. I think it's kind of neat. So we'll see this again on Wednesday, all right? But we'll go over kind of this this idea of the stationary distribution in more detail and deriving it. Okay, have a great rest of your day. We'll see. Have a great Halloween. Happy Halloween. No midterm this Wednesday. We'll have it on next Monday, all right? So a week from today. All right, see you later.